Okay, in this video we're going to talk about Unit 9, Objective 2, Exponential Growth. There's two types of problems that AP can ask with exponential growth. One, they'll ask you to set up a differential equation, and one, they'll ask you to solve a differential equation. And both of them are going to be dealing with exponential growth. So the first thing that we want to talk about is a keyword that's going to give these problems away, and that keyword is going to be proportional. They'll say something like, oops, put on the pen. They'll say something like the growth of population is proportional to the population. And the key word here is going to be that word proportional. So if you go back to Algebra 1 when you're talking about directly proportional, that's what they're talking about here. The growth of population is proportional to the population. So when they say growth of population, they're talking about the change in population. So we would say something like dp dt, growth in population, is proportional, and they mean directly proportional, to the population. So this is going to be Kp. dp dt equals Kp. So directly proportional to the population means some value K times the population. So they could ask you to write a differential equation, and that's what you're seeing on the board. A differential equation is just an equation with a derivative in it. And that would be it right there. dp dt equals Kp. They could also ask something like this and say, instead of the population is proportional to, or the growth of population is proportional to the population, they could say something like the square root of the population, and in that case we would have that. Now, a lot of times if you have that situation, they're not going to ask you to solve the differential equation. They're just going to ask you to write the differential equation. If we go back to the original one, and we'll say that the change in y is proportional to y. So dy dt equals ky. This is one that they're going to ask us to solve. They won't ask us to solve, more than likely won't ask us to solve something like k equals the square root of p, but dy dt equals ky is something that they will ask us to solve. And the good news is we have a rule here that we don't have to do any calculus. If the change in y is equal to ky, so if we are changing in Kentucky, right, ky Kentucky, we know that y is going to be equal to ne to the kt power. So if we're changing in Kentucky, we get to get necked, like we would say it in Kentucky, right? Ne to the kt power, where n, or we'll say y is current value. N is initial value. K is a constant that generally we're going to have to find. And T is time. So NE to the KT. So changing in Kentucky, you get to put your little hillbilly voices on and say we get necked, NE to the KT power. So we'll look at one example of the type we have to solve. Most of these are going to turn out to be calculator questions because we have that E that we're trying to work around. So if we look at this problem here, it says the rate of increase of the population of Springfield is proportional to the population at any given time. So we know right away the change in proportion with respect to time is proportional to the population. So Kp. Now this doesn't say dy dt equals ky, but the p's and the y's can change, and we're basically looking at the same thing. So we know, based on our rule, that p is going to be equal to ne to the kt power. before we even read anything else, we know that that is the case. P equals NE to the KT power. The population in 1950 was 50,000, and in 1980 it was 75,000. What is the expected population in the year 2010? So those first two things that they gave us are points that are going to help us find K. So 1950 and 1980, they're going to help us find. So that 1950, we're going to consider our initial value. That's where we started. That's our original value. So that's going to be N. So 50,000 E to the K, and then we got to think about the other two parts of information. If they tell us the population in 1980 was 75,000, that was 30 years later. So if we plug in 75,000 for population, that's the population quote now, and that was 30 years later, so 30 in for T, 30 in for T. Our only variable left is K, so we can solve for that value of K. So we would want to divide by 50,000, take the natural log of each side, and this is where our calculator is going to come into play. Because on the right side it works out nicely, the natural log and the E are going to cancel out, but our natural log of 1.5, I don't know what it is. So if we're looking at the natural log of 1.5 equals 30K, you can divide by 30, and you get K equals 0.013516. Now notice my K value is going farther than 3 decimal places because that's not my answer. My answer has to be right to 3 decimal places. So we want all of our work to go a little bit farther. So we can take that value of K, plug it into our population function. So population is equal to 50,000 because that was our initial population. E to the 0.013516 T power. And now if they want the population in the year 2010, 2010 was 60 years later, so the population is going to be equal to 50,000 E to the 0.013516 times 60. And if you work that out, that comes out to be roughly 112,503 people. So, if you see proportional, the change is proportional to the thing that is changing, we know that dP, in this case dt, is equal to kp. That's going to turn into NE to the KT, plug in the stuff you know to solve for the things you don't, and move on from there. So that'll do it for this video. We'll see you in the next one.